This is the standard open ARM-100 because you can build it for under $100. Assuming you have a 3D printer, some hand tools, a place to work, and a bit of interest in robotics. It's an open source robot arm developed in conjunction with Hugging Face. We're busy putting together a very advanced control system called Le Robot. And the premise is simple. Robots have been expensive historically because they use very expensive mechanical components because they need to be very stiff. And this is because the methods we had to control them were very limited. And to make that easy, you made the mechanics of a robot precise, very strong, very powerful. And that's all well and good. And it has produced a tremendous increase in productivity. But it's expensive. Nowadays, of course, we have amazing new AI techniques. And there's a very, very real possibility that this will completely revolutionize what's possible. Compensating with intelligent control, which is essentially what people do. The human body is a very viscoelastic system. It's very bouncy, and yet we can achieve incredible feats of precision. Same will be true of artificial systems. One of the hidden costs of building robots, which is easy to overlook, is the cost and time of getting all the other little components that are required to put it together. So one of the unique design features of the standard open arm is that it is made using only a 3D printer and the parts which come with the servos themselves. Servos always come with a few screws and servo horns, and that's all that is needed to assemble this arm. Plus, of course, an adapter board to connect it to your PC. The arm uses 6 identical servos to keep the price as low as possible. Well, I've now seen there's actually a slightly cheaper and older version of this, so you can go even lower. And even in low quantities, these are available on Alibaba for €13.38. There'll be some shipping and tax to add to that when you import them, but nonetheless, it'll end up about €100, and that is projected cost of the whole arm, plus tools, plus a 3D printer, plus some filament, but I'm assuming that you already have those things. However, if you want to make it a little bit stronger and have a little more reach, you can upgrade the pitch servo down here for something more powerful. This is higher up the range. This is an STS3025BL. It's a very nice bit of kit actually, all hard anodized aluminium. This costs 4 times as much though. It will produce twice the torque though. So we shall do a test, see how strong this arm can push down. I've tested it by lifting. It'll lift about 340 grams. I'll see how hard it can push down on a scale, and then we'll change over the 2 pieces which hold that servo in place and test it again. So it's 6 volts. We're just going to push it straight into the scale. 1.5 amps, and then it'll self-protect after a few moments and drop back off. And we'll increase the voltage. Now at 8.4 volts. And again, you can hear the fan slow down as protection kicks in. To change this servo, for this servo, 2 pieces have to be changed. The first section of the arm and the pitch rotation joint. These have been printed overnight. I'm going to peel these, screw them in, reconnect everything, and see what the difference is. As always, when peeling, I recommend wearing some gloves. For the hand which uses your tools, something grippy. For the hand which you hold your pieces with, something which can take a bit of impact. This one's leather, this one's Dyneema. And if your printer is set up correctly, then hopefully these should peel off very easily. Let's see how we did. Not bad. And that's really how hard you want your peeling to be. That is all the peeling required. Print it on a raft if you have a glass plate in your printer, you might not even have to do that. A little bit more on this one because of the overhangs. And one other addition that I've made on this version of the pitch rotation is I've included a 20mm boss, and that means you can fit on a 6704 bearing and I will test if that makes the overall system any stiffer by making a recess for that in the base. I don't think it will make a huge amount of difference, but it may be worth doing so. That would of course break our rule of only using pieces from the servos. But as we are stepping up to a higher power variant, it might be necessary. I'm not sure, I shall test it. So one of my favourite things about this material is that it is both very strong and very easy to peel, which strikes me as a bit of a paradox. Very slight differences in temperature depending on the thickness of the print, and that will affect how much the support layer sticks. So getting that perfect all over, take a bit of practice, keep adjusting your settings, peel ratios and the volume of the extruded bottom layer. As it happens, I have everything maxed out. I have the minimum peel ratio and I have the minimum amount of volume in my bottom print layer that the slicer I use on the up box will allow me. And on the whole, that turns out to be just right. May have a little bit of sticking here. Scrape off any last bits, and we can check and see if it fits. Lovely. And you can see from the screw holes, it does indeed go this way. So that servo sits in there. It screws on to the servo horns of the servo there, and the servo in base will attach to that. Okay, so now I'm going to disassemble this one. And now I'm going to take this one to pieces. You need a P0 for the small screws which hold the servos in place. Two for the base servo on the bottom, two for the base servo on the top. And that pulls out like so. And then here you need a P1 for the M3s which secure to the metal servo horns. So and of course this will have to be released from here. And in fact this wire is also removed. Okay, this is a new one. access V screws. You actually have to remove this one. Okay, now the only thing to keep track of course, is that the ID and the position of this servo have to be set. So this was the old pitch joint. It is number, I think it's number 5. So this is the old pitch joint servo, it's number 5. So the new pitch joint has to be programmed with ID number 5, and it needs to have its position set before those screws are attached. This can then be assembled to the pitch rotation piece and the whole unit put back together. To program our servos, we will need an adapter board connected by USB to a PC and running the Feetech GUI. I have covered that extensively in other videos. So from the debug tab, that's not screwed in yet. So we set it to the middle of the range. And that will line up nicely. So just secure with 8 M3 screws. Screw them all in a little bit loosely first, and then that way you won't push any of the holes out of alignment. Using the longer screws for all of these, that's just enough to do them. Make sure everything's lined up. Finger tight. And now when we move our servo, very strong action. This is not screwed together yet, which is fine, because in order to attach our base servo, we need access to these screw holes here. And that just slides together like so. You can then drop the screws in down from the top. Okay, you now need to connect up the wires. And this is the one fly in the ointment, but at the moment you only get one of these cables with each servo. You can just push these straight in. This then connects back down to the pitch servo, and this one connects off to the base servo. Pitch certainly feels stronger. This arm piece is 50mm longer, which obviously has an effect on the moment arm, but nonetheless we shall repeat our strength tests. And at the moment this servo of course is only running at 8.4, but the other advantage of this servo, this type of servo, is this can run up to 12 volts. This can run up to 12 volts. The higher power variant of the STS3215 of the other servos can also run up to 12 volts. So I suspect the best configuration is to run a 12 volt arm with the higher power 12 volt versions of these, 30 kilogram centimeters torque. And if you really want the pitch torque, one or possibly even two of these back here. Let's see how strong she is. Let's see how we do. So, need to run it at 12 volts. Okay, this is the pitch motor, now running at 12 volts. Not bad. And now running at 14 volts. In the end then, what do we conclude about the difference between these two servos? The more expensive one, the kind of proper one I guess, is about 4 times the price, and that's if we go with volume pricing. At the individual level, it's almost 6 times the price, and that's really a big step up. On flat performance, I don't think we saw twice the torque. The arm is only 50 millimeters longer with the more powerful pitch motor, and the pressing force downwards was not that dissimilar. Peaked with this one at 8.4 volts at about 1.5 kilos, and peaked with this one at 14 volts at about 1.7. But a simple push force isn't the whole story, and the real difference with the higher grade servos is that you can tune the system. You can clearly push this harder, and the main reason for that is because it has better thermal dissipation. The metal case draws heat away from a motor more rapidly. So if this motor was fan cooled, was tuned, and the system was tuned, you could get significantly higher performance for longer periods of time. The peak figures are quite similar, but they fall off more rapidly for these servos. Both servos feature temperature protection, and that's a very useful feature for robots. With normal servos, it's very easy to accidentally burn out a servo because you're not paying attention. These ones will protect themselves, and it's actually quite amusing to see that the servo or some action will push on and release again. And that's a thermal protection loop running in these. For high performance though, you really do pay a premium. Not only is the component cost higher, but the amount of attention to detail it will take to extract maximum performance is also much higher. So perhaps the best lesson to take away from this is that these really are very good value for money. 6 servos plus an adapter for under $100 ex-works, so shipping and import duties, which we just kind of ignore. And you have yourself a pretty capable robot arm. If you want the performance, there are ways to get it. But it's considerably more expensive, and it's quite a bit more work. For most roboticists at this stage, who are primarily concerned with getting software systems to run, this is just a good little unit. Thanks for watching.